performance features. Okay, all right, let's get started. Welcome everybody to our webinar on the Pebble OS. My name is François Baldassari. I'm the founder and CEO here at Memfault. And joining me today, we've got Chris Coleman, who's the founder and CTO at Memfault. Chris, do you want to say a few words?
Yeah, I am super founder and CTO at Memfault, but more importantly, also an ex-embedded engineer at Pebble. So really looking forward to talking about some of the fun bugs that I got to dig into back in the day and some of the systems that we built out. And it's been, yeah, fun pass down memory lane.
Right, of course. The three of us all worked at Pebble, which is why we feel, moderately qualified to talk about it. Hopefully you'll think so. And of course, joining us today is Brad Murray. Brad is currently at Automatic. Brad, why don't you tell us about your Pebble connection?
Yeah, absolutely. Super happy to be here, leading up engineering for the Beeper product over at Automatic, which is what I've been doing for the last 4 years. But before that, was one of the early engineers at Pebble and ended up leading the firmware team for the 5-year run or so that we had between the Kickstarter and the Fitbit acquisition. So really cool to see this code base come back to life and go back through the kind of now almost decade old software that we all wrote together.
I just want to note a few housekeeping items, which is first, unfortunately, we have just 30 minutes for this conversation. So if you'd like us to do a part two, if you think this conversation is great, send us a note after the webinar, and I think if there's enough demand, we'll very happily do a part two. I think we already know we have many more things to talk about than we have time today. The second thing is, if you're not familiar with Zoom webinars, there's a Q&A button that you can click to ask us questions. I know some folks would love for the chat to be enabled. Unfortunately, we've had some really poor experiences with the chat on a public webinar in the past. And so we've kind of learned our lesson the hard way with some pretty unsavory messages shared in the chat in the past. So this is why we mostly use the Q&A function now. Although we'll constantly iterating, and maybe for part two, we'll look for a way to enable chat safely. And today we're going to talk about three things. We're going to talk about why it's notable that Pebble's firmware is open sourced. We'll talk about what it was like working at Pebble, how things were built there. And we'll talk about some cool things in the code base that if you have time, you should look at and why we think they're cool. And with that, let's start by talking about why is this notable? Why is it even worth talking about, right? That the Pebble firmware was open source. Brad, why don't you kick us off?
Yeah, I think it's super notable. You don't really get to look into the history of a company like this all that often. It's again, huge credit to Google, actually. The reason we're having this whole interview is because of Google collected this IP through their Fitbit acquisition, which they collected through their Pebble acquisition. And there's a few people that deserve a huge amount of credit at Google for letting this see the light of day. It's a real commercial operating system. This thing powered over 1 million devices, was in the field for years, and it's really a look at how a team built a product, and you can take a look at it and go through it and see how it all came together.
Yeah, I think it's very rare actually that commercial firmware gets open source. And so it's a rare opportunity, I think, as firmware engineers to look at a real production firmware that's pretty, I think, modern. Yes, it's 10 years old at this point, but I would say that as far as the code itself and development practices, it's still pretty modern and cutting edge. So I think the learning opportunity is huge. And also there's a lot of cool code that hopefully folks will reuse in there. So I think it's very rare. In fact, Chris, I don't know if you can think of any, but I can't think of another consumer electronics product whose firmware, recent modern consumer electronics products whose firmware was wholly open source like that. Can you?
Yeah, I think that's really uncommon. I can't think of any recent examples. I feel like there's been some RTOSs and some other things over the years that have come out that people knew ran on code, but the actual secret sauce or, the years of working through edge cases to get things to wire up, it's rare to see that. I was thinking in my head, there's probably billions of hours of test coverage effectively on this firmware. If you have millions of devices running in the field over many years, that's neat to see and dig into the code comments and understand what was discovered over time.
David Groom in the Q&A had a great answer to the question, is there any other? It's WebOS. Yeah, WebOS was open source by Palm, which was also like a commercial, fully featured firmware that was originally built commercially and eventually open source. We actually know folks from there well because a bunch of WebOS people ended up joining Pebble. So great answer. Thank you, David. Let's talk a little bit about how it was built. So when we think about how this firmware came together, what might be what's remarkable, what stands out as things that either were best in class or unique or maybe even odd about the way that firmware was built? Brad, why don't you start? Oh, Chris, go for it.
No, I think probably one of the weird, like something that led to Pebble being weird is I think a lot of, or not weird, but like unique is that I think a lot of the team was actually formed by people that didn't have like a deep firmware historic background. I'll say that specifically for myself as well. That like Pebble was a startup. It was a YC company. It was a come through a Kickstarter, and it was a bunch of people in their like mid to late 20s at the time, just kind of sorting it out and trying to like hack things together to like meet the next funding deadline, to meet the next milestone. So it definitely, I don't think we necessarily always approached it from like, hey, what does the industry do from our decades of experience? It was more of like, hey, what's a good software project? Let's try to throw that together. So I think that's something that it's a fairly unique where we kind of really approach things from like a first principles kind of experience. And one thing, like since working at Pebble, like working at other places, I've noticed one thing that was really interesting to me was like kind of the platform approach that we took to developing the Pebble product. So what you see here that got open sourced is Pebble OS. It's not Pebble OS for Pebble 1 or Pebble 2 or for Pebble Time. It's Pebble OS. It's the one code base. And if you dig through, there's all of these macros and compile flags that you can build it for every single hardware platform, including all of the development models that Pebble ever built. And this approach like paid huge dividends for us. And we just had one code base that we shipped on everything. And we also had just a running kind of almost agile like release schedule where we just shipped it for all devices every 6 weeks. And that felt extremely good to me to be able to write a new feature, to fix some bug and be able to deploy it to millions of devices, regardless of their variant, really easily, because that's just what we did every day. That wasn't an exception. That's just what we did.
It's so rare. In fact, at any other firmware job that I had before and after Pebble, you started a new program, you started a new code repository, and you might copy paste some code. I shudder to say it, but you might copy paste some code from some other code bases, but you basically started from scratch with every product. And Pebble did that very differently, right? Chris, I think there were some key things driving that behavior. It wasn't just our software brains. It was also, we had some constraints, right? Around what we were trying to accomplish at Pebble that drove that. What do you think?
I think, I mean, from my perspective, I do think there's some software-centric sort of culture approaches or ideas fed into the DNA at Pebble that was very different from places I've been in the past where, I don't think folks would have even thought about like, let's try to support 5 different products from the same code base. It was more of the copy and paste and start from scratch again. But on our side, I think like, to what Brad was talking about, we were trying to maintain backwards compatibility and get feature updates out for sort of all the devices we had built every 6 weeks. And I think that really led to some of the design decisions about how do we make sure everything stays up to date with the minimum amount of effort.
Well, and the reason we did that is we had an SDK. You could build apps for the Pebble and you built one app and it should work on all the models. And so the choices that we had were either to build one OS that worked on all the devices or to build some sort of compatibility layer between different OSs and the app layer itself. And I think we chose to just have one monolithic OS that was compatible with all the apps across all the devices. And that's how we ended up with that platform approach, even though it was really hard. I mean, I'm sure Brad remembers leading the OS 3.0 backports to the old hardware so that you could run like our newest OS when we released Pebble Time on the very first Pebble. And that ended up being a really, really hard, multiple months of work, had to pull some crazy tricks to do it. or adding color to the OS, something we never thought about, which required fundamental reworks on how some of the graphics layers work. Like that was really hard. And if we hadn't had that API compatibility challenge, we might have chosen to have different code bases. What do you think, Brad?
Yeah, definitely. I think like that was a really big thing to like we really looked at Pebble as a platform. And that's kind of like what's our product sensibility, and the software architecture kind of followed from that. Like we had compatibility layers for sure. Like we wanted to, like you mentioned color, like I remember we wrote a bunch of code and we detected that this app was compiled for a watch that didn't understand color yet. But we could still run that binary verbatim that was compiled years before on a color device, and just at runtime we'd say like, oh, this thing, it expects a 1-bit frame buffer to write to. Let's give that app a 1-bit frame buffer to write to. And this is like became this kind of core Pebble ethos as well as a building a platform, is like we do not break apps. I was actually really inspired by if people remember the old new thing, the blog post by the Microsoft engineer. Like they had a very famous kind of similar thing where Microsoft never broke a Windows application, and I wanted us to be the exact same way. To take a quick detour down like the strange bug route, I do remember there's like one case where we broke apps where an app was looking at a time t struct, which is like this struct in C that says like, hey, this is the current time in hours, minutes, seconds, yada, yada, yada. And you can say get time and you get this pointer to the struct. And the funny thing about it was like it wasn't reentrant. There was just some static time t somewhere in the app runtime. And the app was getting a pointer to that struct once and then on a timer re-looking at that same pointer and drawing the clock face based on that, which is totally surprising. You're supposed to ask for what the current time is. Like the time is not supposed to be mutating under you. And so we actually checked like, hey, we changed the behavior here so that this is now reentrant and people got different structs, but this one app depended on that. And that was the API contract we had. So if your app was compiled before we broke that, we would actually bump that pointer just for you. And that was our approach, that we just like, yes, it's gross, yes, it's not pure, but we just wanted to make people's watches work. So that's what we did.
I think there's many other things we did that were very software forward. You talked about the app. Like one of the ways we made sure we didn't break apps is that we had QEMU, the emulator, as a first, like I would say, first class platform, just like our hardware devices were first class platforms. And you could run the Pebble OS on QEMU fully and run watch faces on it and talk to the cloud with it and all that. And every night we would download, a bunch of apps, and we would take screenshots of them through different inputs and make sure that the screenshots look the same as the previous version. That was very software forward. Like, Chris, is there any other thing? We talked about the frequency of release. We talked about QEMU. Any other stuff that you thought was very software forward, whether that's analytics, core dumps, automated testing? Like, what jumps out at you in the kind of software approach we did?
Yeah, I think there were, I guess, 3 things stand out to me. One, I think even relative to places I've been in the past, we had a lot of unit tests in the code, a lot of automated tests in the code that were running to exercise different subsystems, make sure the different pieces were working. 2, I think we did a lot of, or myself personally spent a lot of time collecting a lot of data from the field about what was with an analytics system in there to understand, why might Bluetooth be failing, what problems might people be experiencing in the field, so we could optimize and fix items that were there. I think that was a pretty software forward aspect as well. And yeah, and 3 overall, I think if you look at the code base as we like added new components or as we built things out over the years, it got more and more modular. We used one Bluetooth chip for like the first several years of the company, and then we updated the code to be able to handle a different Bluetooth chip, shifting from starting actually with Bluetooth Classic, and then as BLE started to get adopted, moving over there. And I think there's many examples within the code base of these refactors and these efforts over time to build out the platform. So it's easier, I'd say each project is becoming easier and easier to swap out components and bring new capabilities in.
Chris, you're perfect. You gave me the perfect transition to cool bits of the code base we want to talk about. Brad, let's start with you. What's your favorite part of the Pebble code base? What's something you're particularly proud of, or you think is particularly interesting, if not a source of pride?
I think it's got to be the app sandbox. I think the way that we run apps is pretty compelling. It was a lot of work, like going all the way back to what was it, like 2012 when we first launched the Pebble SDK. It was nascent. Like
There
literally,
was
it was
no
like
sandbox.
no, there it was a pile of Python scripts that allowed you to statically link an app against our firmware. And so if
You
like on
dereference the null pointer and you would crash the whole watch. That
not even
was
that,
just
you'd have to recompile if we had a new firmware. Like the new
right.
versions were like so wild, like that we bothered to ship them. But like we had just such an enthusiastic crew of hackers that were following us along that we didn't wait for it to be good to ship it. We just said, hey, go nuts. But obviously, as we started scaling, like this wasn't going to work. Like just being able to like overrun and blow up all the firmware and crash and like also like we're dealing with a lot of like students or like really enthusiastic people that don't necessarily come from a firmware background like ourselves, and learning C was like this huge effort. And we were kind of teach people being like, oh no, don't like you can't use a pointer after freeing, you can't do that. And it's like, what? And so like these kind of issues and having your whole watch reboot made it so much harder to debug. So we ended up building a system where we could basically, whenever like apps were still running on the native instruction set, they're still compiled for the watch. Um, and like you'd basically restrict the permissions on the MCU and then jump into the app kind of trampoline to start things up. And from there, the app would be running on the raw CPU and time sharing with the core OS, but in this lower privilege mode when you can only write inside your sandbox. We wrote a bunch of tooling to make it really easy to expose functionality to that, to expose libraries to that. And we wrote it all ourselves. Like it's not any kind of standard linking or syscall interface or anything like that. So there's a bunch of code gen in there to do that. And overall, I think it worked out pretty damn well until we moved on from using C as a language in general for app
Chris,
development.
Chris, do you remember how would we prevent if an app dereferenced a null pointer? How do we prevent it? How do we prevent that from crashing the whole OS?
Yeah, so I mean, on that side, how did that work? If an app made a bad access or a thing took place, it would effectively trap into a fault handler, a usage fault handler, where we'd say, "Hey,
Yeah,
this
the
went
normal
down the wrong
firmware fault
path."
handler that ARM has on
And
every
I
chip.
think actually that's a very interesting part of the code to look at, because normally when you hit a fault, you just reboot the device, right? But this is actually an example in the field of you hit a fault, we'd check and see like, is this coming from the application task we were using FreeRTOS that's running? And if it was coming from the application, we would effectively clean up the state, exit the application, and return from the fault handler, which I don't I don't actually know if there's like any, or I can't think of another example of that out there in the field of like people sort of leveraging that functionality.
Recovering from a usage fault on a firmware device, like just continuing to work because you know that it's happening only in very well sandbox or very well sandbox quote unquote software. Brad, one question for you, which is why didn't we go a VM route? Do you remember? We investigated. I remember, for example, there's a person named Elizabeth Scott who had built a whole sandbox for these like block-based board game devices that were built by a Media Lab spinout. And I found it very inspiring. It was completely custom VM, but we went a different route at Pebble until we eventually did the JavaScript thing. Why didn't we go VM with the way of the VM?
Like in terms of like app execution, basically.
Exactly.
Yeah, so I think it's just a matter of resources. Like you have to remember, like this microcontroller we were using, it was tiny. It like felt
128K of
tiny at the
flash.
time.
The first one was 128K, right?
Yeah.
That's all we had.
And like an absolutely tiny amount of memory and very few resources, and just like not a lot of like the chip had some like interesting modes of operation and some really great tools, but they're all very basic. And so we were able to like, and also we wanted to expose people to the full power of the watch. I think we gave people like 32K total like code,
Right.
like because also like the actual app binary itself had to be loaded into RAM to be executed. So like how big your clock face was, like if you made it bigger, you had less RAM to actually run your data. So like we wanted to really eke out every little bit of power, and kind of we exposed this like really high level power interface and this like really powerful UI and layers and components and all that kind of stuff, and it made it look like you are like writing HTML or Qt or something like that, and then you throw it on this device and you realize how little you're working with. So everything was really thin to the bone, and we just got away with like these kind of custom fault handlers, a very simple memory protection unit, and
We were big users of the MPU. That's like another interesting kind of
yes,
aspect of the code base to look through it. I do feel like I digress, but I feel like looking through the code, sort of how deeply we use some of the peripherals from ST, like actually like maximizing all the DMA pieces, how deeply we went on some of the ARM architecture stuff. I think it's great examples of that in production that just I don't see much of.
yeah, and also
Um,
just kind of like we just had this chip and we just knew what we wanted to do with it and we just pushed it as far as possible. And like that's the thing, like when you have millions of devices in the field and you have this new idea for what you want to do, it's not like you're architecting that into the hardware layer. You're going to see how far you can push what you already have.
Chris, moving on to your favorite or most notable part of the code base, if you had to pick one, what's the thing you'd highlight?
Uh, probably strictly because I spent a lot of time in that corner. I'd have to talk about the NOR Flash file system that's in there, the Pebble file system. If folks have ever used NOR Flash before, you know, if you keep hitting this, it's just like on its path to death. Every time you erase a sector, there's like one less erase that part has. And something that's really important is wear leveling. We had a ton of files that were different types of files that we were saving and loading and storing within Pebble applications, settings, logs. I can kind of go through the code and look at those, but we built a layer on top of that, about 10K of code that managed the flash underneath. So it was really easy to make sure we're getting the right wear leveling, really easy to look up files within there. That's an area I'm excited to see to take out of the OS and see if we can sort of drop it into other places. It's pretty agnostic.
It was a rewrite, right? If I remember well, I think we were using the Contiki. So
It was the one in
Contiki
Kentucky.
we had looked at all the open source kind of embedded file systems, and the fat file systems just weren't working for us because they were very big and the access patterns were very different. And there were a few non-fat file systems, but they were kind of all of them were non-production ready. And we had started with the Contiki one. Contiki is an RTOS that they also wrote the LWIP stack, which became the de facto IP stack in firmware, written by Adam Dunkels.
There were two parts I remember at the time about Kentucky that like made it sad for production use cases. Like one, if you had too many files, it would get into this insane garbage collection loop where it basically just sort of like tear through and move things around on the flash where like you'd try to allocate for a 4K file and it would spend a minute erasing flash sectors. And then the second one was it detected the end of a file by reading backwards from the sector until it didn't see FF. If you've used like, or basically it didn't see bits set to 1. If you use NOR Flash, you know, you can change from 1 to 0, but not a 0 to a 1. And I remember a bug with our application installer where if we had UUIDs that ended in FF or ended in an F, we wouldn't be able to load it because Contiki would like think the end of the file was like a byte before.
That's right.
brutal. And
Yeah,
also like Kentucky was like used for a very brief time, if I remember correctly, but because before that there was no dynamic file system. There's literally just like I think I just had like a piece of
regions of
paper on
flash.
my
The
desk.
block
And it's
storage
like
sort
this
of.
is the flash, this is how it's all divided. There were 8 app slots. There was fixed size for how big they could be. And I think we tried to do the Kentucky thing to break that limit. I think actually the funny thing, Tyler did that work. But before that, we just had no file system. We got pretty far with that. Um, Maybe that's another thing to touch on. Like we did a lot of things very simply until we couldn't do that anymore. It was like a very big Pebble motto to do the dumbest thing that could possibly work. And you'll see quite a bit of complexity and interesting cases in there, and that's because the dumb stuff didn't work anymore. But there's also some really dumb stuff in there too.
Yeah,
Another
but
kind
you
of
see, like constantly we did that, right? There was if you think about the file system, we started with no file system, then an off-the-shelf file system that was meh, and then eventually a custom one written from scratch. Same thing with the heap. Mark Jessam, right? Like basically, replaced the FreeRTOS heap with something that was more or less custom built. I think it was inspired by an open source project. And same thing, like eventually fragmentation was too big of a problem and we need to invest more in that. And this happened again and again. Another good example, my favorite part to show people of the Pebble OS is the serial protocol, the Pulse serial protocol, which was, I think the most complicated serial console that has ever been written in a firmware device, right? It could do, it did binary logging. You could get screenshots over serial with CRCs and retry and reliability baked in so that it would, you could get core dumps over serial, you could push firmware updates over serial, and it was an extensible protocol. And that also, we started with like just a serial console, and then we added commands, and then those commands started doing wonky things, and then reliability became a problem because our tests would fail due to a flake on the serial. And then eventually we ended up with this like 2,000 line of code serial console that I think you can reuse.
The big thing was like resource imaging, right? Like we would actually, like as part of it, you would update the firmware, and then you would put the serial console into a mode where it would accept bytes and just write them through to the flash over the serial UART. And I remember we would have tests fail because like someone would have like a puts out raw to the serial like while the resources were coming in, and just the whole thing would explode.
Chris, you want to tell us just a tiny bit more about what made the Pebble file system unique?
Yeah, I think one dimension that makes it unique is it took full advantage of the fact that you were working with a NOR flash. That like basically once you write something, you can't sort of reset bits from 0 to 1, and so it let you sort of take advantage of that abstraction. If you don't keep that in mind, you wind up, the way it works under the hood most of the time is like if someone's trying to just like open a file and write over what was already there, you wind up burning a ton of like cycles erasing the block and then copying the data to a new block. And we were putting together a bunch of features where that just took erasing NOR flash is slow. And that just took too much time. I think like one of the examples that probably you'd have the most context about, François, was some of the internationalization aspects and like how we were able to save large font packs on the flash and load them in time to render characters in different languages as they're coming on the screen.
Let's touch also briefly on another component I like a lot, and which, of course, at Memfault is something we thought a lot about since, is core dumps. The Pebble OS, did core dumps because, frankly, releasing software every 6 weeks, super complex operating system, we had so many problems. I mean, it was Bluetooth problems, it was battery problems, it was memory, file corruption problems. We had so many customer support requests that sometimes it took our 7 or 8 person support team days to get back to someone because the volume was so huge. And Chris, you want to tell us a little bit about how core dumps work? And Brad, maybe you'll touch on analytics, since that also went hand in hand, and I think you worked on that a good bit.
Just really quickly before Chris does it, deadlocks. That was the big core dump thing.
Deadlocks happen all the time. Mutexes.
All the time.
We
Debugging
started
a
by
deadlock
putting
without a core dump, disaster.
we started by putting like last held mutex in the reboot log, right?
Yes.
That was the very first version of that.
Yeah, we were, I mean, probably from some software first principles, but we were heavy users of the capabilities of free RTOS, having tasks, having locking, having things in place. And as a result, yeah, the core dumps were invaluable for when there was a deadlock or when things were in the field. Common, I think approach most folks would take, basically a fault handler would get kicked off. We'd scoop up the information. We had a little script in there that would decode it, and we could start to unwind what was actually taking place on the device. So I guess the bugs that come back to me were deadlock classes of bugs. I think we had a really good software watchdog implementation in there to catch the deadlocks or catch sort of like hangs or problems in the first place. And then there was also, we were heavy users of malloc and heaps inside the OS, which I think it's actually interesting because we had such a small amount of RAM. There were many sort of things that no one was ever running in parallel. And it let us kind of push the limits of the number of notifications we could batch or the number of things someone could see when the watch was in a certain mode by using dynamic memory. But as a result, there were memory leaks and pieces that getting a core dump of that so we could walk through the heap and figure out what was taking place was invaluable.
One thing that I remember is that we would crash the watch on purpose sometimes. We had parts of the code where we know, like, if the watch gets into this state, something very weird has happened. Let's crash in order to get a core dump so that we can debug this problem. And we did that with Bluetooth all the time. And it was really effective. And in fact, I think the Pebble watch to this day, like had a great rating on Amazon because the Bluetooth was so reliable in an era where Bluetooth just didn't work for a lot of devices.
The other thing we did was we made it really loud on beta builds, where when it reset, a notification would pop up
that said we
be
reset.
like, hey, this reset, this crashed, like contact the team. And I think that like really helped in field testing, just getting reports right away for something a person may not have noticed or thought to report.
And beyond just beta testing as well, like we shipped certs in production, which I still think is strongly the right thing to do. I know maybe that might be a controversial topic, but like crashing the device is so much better than trying to like recover from this uncodable experience that we're not handling.
100%.
Running while broken is worse than crashing. Crashing is very fast. The Pebble OS booted in a second, basically, right? Most users didn't notice crashes unless we
you
you
also don't fall into like the 7 layers of errors that happen if you like compile out your
Cloud
asserts.
memory corruption, and
when the thing finally blows up, it's like, how did I even get here?
Exactly. You can sometimes kind of limp along, but bad things will eventually happen. Let's talk about we're at time for the main part of the conversation. Once again, if you want more of this, just send us a note. We'll probably do a part 2. I'm having a lot of fun. We have a bunch of questions. Chris, go ahead.
I was just going to say next time, like what we'll have to do is favorite print line. But as I was like looking through the code when it popped out, there was, if you see this error, please let Brad know.
Still there. Search for Brad. It's still there.
And also least favorite module, Daniel Rodriguez, one of our ex-colleagues from Pebble, said, like, what about the things you wouldn't do again? I think that would be a very interesting question. Maybe we'll touch on it briefly in the Q&A. So let's start with the Q&A and say, first, we have a question from Matt Campbell, who asked, did the software approach affect our hardware design? So maybe in other words, in what way did we make non-traditional hardware design decisions that were informed by this very software-forward approach? Brad, do you want to start with that?
I think Chris would be better situated to answer as the most software-y of the three of you, for sure.
Got it. Chris, you're up.
To the software, I guess something that came to mind in my head is I feel like relative to other places I've worked in the past, when we had sort of early prototypes, like when EBTs came available and things were there, due to the software forward approach, there was already a way more functional device than I typically see if you're sort of like starting from driver bring up or trying to exercise what's in place, where I felt like it helped us get to the bottom of like, were we going to meet the power goals? Were these like devices going to work? Because more of the code had been developed and tested, and we knew it was going to work there. That's sort of one aspect that came to mind.
Well, there's a few things that come to my mind. First is I think many firmware engineers on this call will have fought their hardware team for more flash, for example. And generally at Pebble, the software team did have that voice, and we were really able to advocate successfully for more CPU, more flash, like making the firmware team's life easier was part of the design consideration, right?
It's a good call out. Like when we switched chips or like when we switched Bluetooth chips, like a requirement on the list like that we're involved with is like, what's the debuggability of this chip? Like what information does it expose that we can look at? What's the tool chain that's being used? I guess that's actually different than places I've been at in the past too, where there is a really strong collaboration between the electrical engineering team and the firmware team about the design, about the component selection, which you don't see everywhere.
And maybe building on that too, like this platform approach, I think we tried to stay in the same families unless absolutely necessary. Like if you're rebooting your code base every time, you can pick whatever new microcontroller from whatever new provider, but like make it easy on us, please. Like if there's a newer one that has more flash, yes, please. If it's an entirely different family, I don't know, there should be probably a pretty good reason for adding support to it.
And then the second thing, and all credit goes to Nick Ford, who is an incredible electrical engineer who thought a lot about software engineers. The big board, which was the dev board we used for Pebble, was extremely well suited to doing automated testing and development. So for example, one thing that Nick did is he put a 4-channel FTDI chip on the board, and one of the channels was basically an I2C bus on which there were a bunch of current sensors. And so you could basically run a version of the OS, an app and all that, and live stream current readings from all of those I2C current sensor and then plot them with a little Python script. And that allowed us to do very good power analysis with like we could basically test the power of every pull request automatically. That was very, very software forward, and I thought really excellent. And I still miss working with Nick in that regard. He was just very, very software aware.
The INA 226, great part for dev boards.
Blake asked about Rust. I was wondering whether we'd get a Rust question, which is, do you think they're going to start rewriting parts of Pebble OS in Rust?
This was you at the time. Weren't you screwing around with the runtime-less Rust thing in 2016?
I did mess around. I did do, I built a version of our SDK that let you write Pebble apps in Rust. We never productized it, but we might have open sourced it at the time. And I did a watch face fully in Rust. But at the time, Rust didn't really do the no STD. Like Rust hadn't been didn't yet have the right hooks to do embedded with Rust all that well. And today, I think it would be a great idea to maybe write future modules in Rust, but rewriting big portions of the Pebble OS, I think there would be no benefit to it. It's code that has been really battle tested at this point, as much as I love Rust. Next up, we've got Austin, who asked 3 questions. First one, love it. Are there any fun Easter egg you remember embedded in the devices? Anything that jumps out, like whether a comment or log line or some Easter egg that you could, with the right button Konami code, that you remember?
It's fun searching through the comments. I'm trying to remember what else. I'm going to steal ahead from the other questions. Justin asked about or mentioned the WTF macro. Mm-hmm. That was our macro for just immediately crashing the device whenever something went wrong. You just write WTF in the code, check that in, and that would take care of it.
Chris, any Easter eggs that you remember? I don't have anything off the top of my mind. Maybe we were particularly boring people at the time.
I'm trying to remember. I mean, there were definitely some button sequences that would like put the thing into like a factory reset mode or force a core dump or force collection. I was trying to remember. I thought we shipped one Easter egg one time, the new feature, but maybe that was in the mobile app.
Yeah, I think we had a few like April Fool's runs, but I think that was mostly run through the web team. I think as
yes,
people were
it was so much easier to ship an update. And then both Austin and Philip asked something that we've actually discussed in our pre-prep, which was, you each get to tell us a story of one bug. We're gonna have to make sure we don't spend hours on this, but Chris, why don't you start? One biggest bug that you remember to this day that was kind of a story you had to get to the bottom of.
It had been several years. Our devices have been out in the field, and we started to get an uptick in support requests where people were complaining that the assets weren't loading, the resources weren't there. They were getting sort of sad watch face failures. And we started to RMA and send them in. And at the time, as the frequency came in, it was a little bit concerning because it was like, oh no, are all these like devices that are out in the field dying today? And spent a lot of time digging into the different layers, trying to understand what's there, looking at the different CRC patterns. Long story short, we were not waiting enough time when we're waking our NOR flash up from its low power mode before we were issuing writes. And so as the flash had weared down, the like charge pumps like didn't have enough time to get to the voltage level they needed for the bits to actually set. And so like any good bug, one line fix, there's a delay 100 microseconds in the code when waking things up from low power mode. And it fixed this fairly significant amount of devices we were getting week over week that had hit that age lifespan where they were failing. I thought that was a really cool software fix.
Those are always very interesting bugs, right? You're slightly out of spec and you're fine when the devices are brand new. And as they age, they start becoming more marginal to the spec, and all of a sudden your code starts failing, sometimes really loudly. And sometimes it's all the devices within a week of each other start failing in that way. It can be very dramatic. Brad, what's your favorite bug that you remember? Or least favorite, I guess, maybe.
I think my favorite one, that was just the most clever one, that was actually a security bug that came through the White Hat program. The way that the app sandbox worked is that, of course, like you couldn't compile your whole every code instruction ever that your app needed into that 32K, you needed like libraries and drawing routines and you need to call into the operating system. So we made this syscall layer where unprivileged app code could call into our libraries and draw a circle or something using our code. And the way that we set it up is that if you were running in your unprivileged area, we didn't trust you at all. But then if you were running our code in the library, you could do whatever you want. And it was just on us writing the library to kind of sanitize all our inputs and be really safe and go like that. So basically, if you're running from our code, you're trusted, you must be the right person. If you're running on the app side, you can't be trusted, you're scary. Someone figured out that we didn't actually protect the region of memory that stored our fonts and resources in. Actually, no, it wasn't memory. It was in the microflash itself. It was in the binary itself. We had baked in a few fonts so that if everything went totally wrong, we could still print a font to the screen. And someone found a series of bits in the font that was in the code that if you interpreted them as ARM instructions would jump back to any arbitrary location. So this effectively allowed an app, if you jump to this random address, to have code execution returned back to you in the app sandbox, but you have all the privilege bits set. Great
That was an
bug.
amazing bug.
Great bug. I have no idea how someone found that without looking at our source code. Really eye-opening for like how broad and how full you have to think about security posture and making it work well.
And do you remember how we fixed it?
We memory protected the region. Like you
Yeah,
shouldn't be
we
able to
made it
add on.
non-executable. We still needed it to be readable from unprivileged, but we made
Yeah,
it
it was the
non-executable.
constant area of the flash. We just started memory protecting that area as non-executable.
It's where reading the MPU code in the code base. It's fun.
Brad, here's a one that's just a tee up for you. Why on earth did you
I know where
choose
you're
the
going.
WAF build system?
The WAF build system came to Pebble because I had been hurt before. It came to us because at the previous company, I was actually the maintainer for the makefiles that built this massive thing, and build times were slow. They were undebuggable. Makefile syntax is insane. It's not even syntax. It's barely syntax. It's like space delimited. If you use tabs, it doesn't work. It's insane. And I just thought there just needed to be a better way. So I got a little innovative and I got a little creative and I found this Python-based build system that to this day I will defend as being mostly fine. It's very powerful. We built our SDK based on it. Our colleague Sherry actually did a talk at one of our developer retreats about how all these interesting ways you can extend your app builds with using the WAF build system. And really, like there is a ton of configurability in our build. Like the Pebble build is quite complicated. There's a lot of different flags. Like just type WAF help or whatever. There's so many flags, and I think WAF helped us manage that complexity. But on the other hand, it's very boutique and weird, and nobody knows it. And I don't know if it's the fastest thing in the world. And it caught me a lot of flack working at Pebble, having chosen and defended this build system.
Instead of
It
being
was
the makefile guy, you're now the WAF guy.
Which was better. Honestly, it was so much better.
I found it turns out I think for me that having the full power of Python in a build system is a foot gun. Like
I disagree.
you end up putting so much logic, doing so many things in your build system that maybe it's better to have those be escapes to scripts. But reasonable mind can disagree. And the thing that I found most frustrating is that any kind of small deviation from a very standard compile this C code using a C compiler into an object file, if you wanted to modify that flow, WAF was so dynamic and made so many assumptions about argument names and things like that, and did so much magically under the hood for you to associate those files together that you had to become an expert in WAF internals to even figure out how to like add a flag in when those things were
Oh, fully. I
compiled.
remember telling
And I
you,
found that really difficult.
you're probably saying that because I've asked you. It's like, oh yeah, like you want to know how to do that? Just read the source code. It's not that bad.
Exactly.
I think that's what all build systems degrade into, though. Like all build systems are flawed. If you have a project that's been running for long enough, eventually you have to like dive into the code or the internals or whatever to understand what's there, how to extend it. And I don't know, like the disadvantage I see with WAF is there's just like fewer people who have gone down that journey versus like CMake or Make. But like as far as like build systems go, I feel like we eventually face the same problems. I was surprised to see it's still an actively maintained project. I cloned it last night and was reading through the commit history for old time's sake.
We're going to do 5 more minutes and then we'll eventually have to break. But so I'll ask you a couple more questions. The first one from our ex-colleague Daniel. Hi, Daniel. So let's talk about each one thing that you would definitely do differently next time. One, piece of the code that's you're like, okay, I learned my lesson, if any. Chris, you want to go first? I see Brad in deep contemplation. Brad, maybe if I give you, I can go ahead. I'll let you go.
I feel like the early code base was just like so rough. I think maybe like it's hard for me to remember because there were so many mistakes made and we actually just kind of fixed a lot of them iteratively over time. Like it's kind of maybe it's for the best, but it's kind of a shame that the commit history isn't there. Like it'd be so interesting to be able to go back and look at the code base in 2012, 2013, 2014, 2015, 2016, because you're kind of seeing like a pretty polished outcome and not all the mess that we made along the way.
What about Pebble protocol? I think that maybe that's a thing where we learned a lot of lessons along the way when we designed Pebble protocol, right? It's like, I think one of the things that I wish we had done earlier is some sort of schema definition that could be shared between the firmware and the mobile on the other side. That feels like something that was in a way a design mistake. Your design mistake, Brad, if we were gonna point a finger.
Well, it's so simple. It's like a 1-bit type, a length, and then a bunch of bits, and then good luck. And then you just shove whatever you want in there afterwards.
But
To
basically,
me,
synchronizing the definition of these data structures across different code bases was a constant problem for us.
Absolutely.
Chris?
I think the interesting thing, and I guess it's where the commit history would be good to look at, is what I was thinking about in my head is some of these things we added in the middle, where there was probably some dumb first approach we could have like gotten out the door that would have been invaluable to have earlier in the project or earlier into the project. So like I spent a lot of time with Bluetooth, so things that come to mind for me is when we're really trying to optimize the throughput. So our out-of-the-box OTAs were quick, or when we're really trying to get to the bottom of like connectivity issues. Something I wish I had earlier was metrics about like what was in place or what was happening there. And that actually kind of came in, I think, a couple of years into the first project that's there. Where if I were like starting again, I'd think about like what's the simplest thing I can get initially for information like that. And then I do think we spent it. The only second one real quick is I think there were a number of driver sort of abstractions that we put in place over time that were like super invaluable as we were like swapping out accelerometers or swapping out Bluetooth chips or like using different components that for like putting it together again just would have like had something simple there from the start.
I think, by the way, I talked about Pebble protocol. For those of you who are not familiar, Pebble protocol was the Bluetooth application layer protocol between the Pebble OS and the phone. It was basically the Bluetooth API to talk to the watch. I think I'll tell you one more thing that for me is something that was a pain in the butt and I wish we'd done differently, which is also a data structure synchronization problem. It was the analytics payload. If you remember, when you logged analytics, there was a big struct in memory for all the different analytics entries we wanted to track. And then we sent that struct once an hour, basically. And they were just all metrics, right? Battery drop in the hour or things like that. And then that struct went to the Pebble collector, which was a cloud application which received that analytics and would then turn it into entries in a database that could then be queried, right? It would basically translate the struct into something web tools could understand. And so the firmware and the Pebble collector had to be released in sync so that struct definition was shared between those two, and it was manually edited, and it was constantly breaking. And so you'd ship a new update version of the firmware, and all of a sudden we had no analytics. And that seemed like, at Memfault, we've designed things completely differently, where the firmware binary actually contains the analytics definition. So when you upload your symbol file, it automatically will know how to decode the analytics. And basically making sure that there are ways to share a definition between your firmware and other parts of your stack was a big lesson learned that I think it took us way too long to learn. Okay, so unfortunately, we're at time. There's a couple questions that are very easy to answer, so I'll just talk about them super briefly. Is the dev board hardware open source? Unfortunately, none of the hardware is open source, basically. So in fact, the new Pebble project that Eric is leading is all doing brand new hardware designs. And do I have any other thing? I think that's the only question that I can answer. Any thought about Platform IO? I think Platform IO is cool. I wouldn't use it for a project as complex as Pebble, but we can talk about that another time. And someone has that commit history. Maybe it could be uploaded. That commit history is a Google-owned IP, and so I cannot suggest that anyone does that. It would probably be some sort of confidentiality breach if someone did that. But you do you. And Ryan just asked about Renode instead of QEMU. I will say that Renode is excellent. If it supports your specific set of CPU and peripheral, I would go Renode 100% of the time. And I've written at length about Renode on the Interrupt blog, how to set it up, and we use it a decent amount at Memfault. And with that, unfortunately, I have to wrap it up. I will try to email some of you answers to your questions, time allowing. Thank you so much for having so many of you join us. Stay extra time, ask us question, email us at webinars@memfault.com. If you want a part 2, we'll be so happy to do it. And in closing, I want to thank my co-founder, Chris, for joining me today. And of course, Brad, who's taking time out of his busy day to reminisce about Pebble with us. Brad, it's such a treat to get to chat with you and think back on the amazing work and times we had all together at Pebble.
I hope there's a part 2. This is really fun.
Yes, thank you guys. Super fun.
All right. I hope everybody
everyone.
has an amazing rest of your day. We're gonna close this out, and you'll get all kicked out of the webinar. But it was a true pleasure. Bye, everyone.